Good morning, everybody. Just wait on Morgan to log in, and we're good. Oh, hold up. Let me switch to my hotspot just to be on the safe side. Hopefully, it won't log out. All right. So when we left off on Monday, we were talking about using this hydromethylation technology to transfer alkyl groups, and make sure this thing is recording. Yes. All right. So one of the methods that we looked at was using this thexoborane, but it was substituted with an alkyl group, right? And you were able to from this method get a cis alkene. All right. And so let's talk about how that works. We already kind of went through a couple of mechanisms dealing with this. So let's look at how this one works. And I'm going to start at the um, I'll start at the iodonium ion, right? Because you got iodine and your thexoborane is going to add across. So we're going to start here because we've already seen the addition steps, right? So it's here. So my borane is here. Right? And then you can see from this intermediate that the borane and the R are on opposite sides. So it's not cis yet. So it has to be something that happens within that mechanism that's going to cause it to be converted into cis, right? And so, of course, this iodonium ion now is going to react with the hydroxyl group, but instead of the hydroxyl group attacking a proton or popping the ring open like it did in the last example, the hydroxyl group is actually going to attack boron. Right, so this is coming in here like that, and it's gonna generate uh, a negatively charged boron, which then is going to be set up to eliminate. So but before it eliminates, it's going to transfer that alkyl group, right? So your new intermediate looks like this. This is iodine. Thought I had this glove issue solved, but obviously I don't. I gotta find a better non-palm glove, whatever it is, because this one is crap. So here's my boron, and then my thexyl group is still here. And now this is OH, and my cyclopentyl group, right? And now this is negative, right? And so in the next step, what actually pops the ring open is transfer of the alkyl group. So this alkyl group is actually going to transfer to here and pop that ring open. All right, so now I'm left with this intermediate. So my iodine is here. R group is here. And then my borane, let me fix that. Sorry about that. It's here, like so, right? And then my cyclopentyl group is here, right? So I can't eliminate because again, it's either going to be syn periplanar or anti-periplanar elimination. And so boron is not in a position to do that. So I add another hydroxyl group and it's going to attack boron again, boom, here like that. And so I end up with, let me move this over some. So here's my borane. Now it's got two OH groups on it. And it's negative, which is going to facilitate that bond rotation and elimination. So this is H. This is, sorry about that. Right. So in order for this to eliminate anti-periplanar, where does the boron need to be? Keep in mind it's eliminating along with the iodine. So if it's anti-periplanar, which position does the boron need to be in? And how
Would it be equatorial?
go again? Go ahead. My bad.
Would it be equatorial?
Well, not necessarily equatorial, but you want it to be anti. So it needs to switch places with that cyclopentane,
Okay.
right? So
All
I
right.
need to rotate the bond so that that can happen. So I'm going to rotate it this way, like that.
All
And so when I do that, That's going to give me the iodine. It stays put. All those groups on that side stay put. So this is R, H. But now my pro cyclopentane is here, and then my H is here, and then my boron. I need to move that. My boron is now going to be pointed, and it's going to be in an anti position, anti relative to iodine. So I'm just going to put B. It's got two OH groups on it, and I'll just write in thanks, right? And it's negative. So now you can eliminate here, like this, and then here, right? And so that's going to give you your cis alkene. This is R, and this is the cyclopropyl group on the same side, right? So that's one way of using this technology even to transfer alkyl groups. And if you look at the alkene, right, you could probably have done that through a Vidic or through a Horner-Emmons reaction or through a Peterson alternation, but we didn't start with a carbonyl, right? We started with an alkyne. And let me put a couple of arrows here so you'll know that this is not the first intermediate, right? So we did it using the alkyne. So all of this is a part of the alkynes to alkenes technology that we started talking about. So we got one more reaction to talk about with these alkynes, and it is hydrozirconation, right? And just like it sounds, it's using zirconium, a zirconium metal species that's going to serve as your hydromethylation agent, right? So let me show you, uh, give you some information on that, and then I'll post the hydrozirconation notes. I'll post that in the course notes today. Uh, yeah. So let me show you. Let's talk about that. So hydrozirconation of alkynes. All right. And so first of all, the zirconocene catalyst is in this case what we call Schwartz reagent, right? Or Schwartz's reagent, right? And it takes advantage of a couple of things. It takes advantage of the one of the pi bonds being able to bond to zirconium, and then also being takes advantage of what we call back bonding. In other words, the empty orbitals on the zirconocene or the pi star on the in the pi system can also interact with the sigma bonds on the zirconocene. So let me show you. Let me show you that. All right. So normally this is written like this: CP2 ZR HCl. Right. The CP2 is actually a cyclopentadiene. So it looks like this. Right. It's an aromatic, negative charge, negatively charged cyclopentadiene, and that's coordinated to zirconium. You got two of them coordinated, like so. And then it has chlorine, and a hydrogen attached, right? And so the this with a triple bonds are capable of back bonding because they have um, p orbitals vertical, and they have so on the y-axis and on the z-axis, right? Because you got the two pi bonds, and each one of them is made of two p orbitals. So this can you can have a bonding interaction between the zirconium and the p orbitals, which will look like this. Let me zoom on that so I can draw those right. All right, so these are my carbons, right? And then I have the zirconium here, right? And so you get an interaction here, but then you also have like what's called a back bonding interaction, and that's normally with uh, the pi star orbitals on an alkyne, or it can also you mainly see it on alkynes. You can I mean it can happen on an alkene, but normally you see uh, this back bonding with alkynes. You see that a lot, especially when you make like cuprates and you have a alkyne substituent on a cuprate. We're gonna talk about that later. That's the reason for that is because that back bonding is pretty. It's a significant interaction between the metal and the carbon. So uh, in this case, with the zirconium species, it's the HCl part that participates in back bonding. So it's the so it's a sigma. Let me fix that up so it'll look halfway decent. All right, this is your chlorine. All right, and that's going to interact with the pi star of your alkyne. All right, so it's going to be sigma donation into the pi star. So that's how your back bonding works. It's the pi star orbital of the pi system, and then the sigma system of your not your organometallic. Sorry about that. Your zirconocene. All right. So when you look at hydrozirconation from the perspective of like the optimal substrate, right? The optimal substrate is going to be an alkyne, right? If you do it on an alkene, it's just going to dehydrozirconate. Or if you do it on a branched alkene, a long chain alkene, it's just going to do what's called chain walking, and I'll show you that in a second, right? But your alkynes are your optimal substrates, right? And then terminal alkynes react the fastest. Right, so your optimal substrates are going to be terminal alkynes, right? And then terminal alkenes, which are comparatively uh, as reactive as disubstituted alkynes, right? And then you have trans alkynes, which are also reactive, but not as reactive, right? And then one disubstituted alkenes, which look like this, and then trisubstituted alkenes, which are the least reactive for obvious reasons, right? This is a very sterically hindered alkene, and so yeah, that's going to be the least reactive. Um, you can also do this selectively, where you have a enine, and the zirconium will hydrozirconate the alkyne before it hydrozirconates the alkene. Right. So let me show you that. Right. So if you have this enine and you treat it with the Schwartz reagent, right? And this is pretty mild toluene at room temperature. Right. You get selective hydrozirconation, where the alkyne is the um, only functional group that undergoes hydrozirconation. Right. And then you can also do this on, and this is a great strategy. And this was done by Friese 1991. And this is in JOC, page 7201. You can also selectively uh, hydrozirconate alkynes, right? If you put a TMS protecting group on one end, which is possible, right? That the pKa of that alkyne proton is about 25. So if you treat it with a decent base, you can remove that proton and protect it with a silicon protecting group. Um, Treat this with the Schwartz reagent. And this is in benzene at room temperature. Right, your hydrozirconation only takes place on the unprotected end. I'm just going to abbreviate this. Right, it only takes place on that uh, unprotected end. And this is done by Crombie. And this is in tetrahedron letters. 1987, page 4875. Right. So one of the functional parts of this is that you can actually convert the vinyl zirconocene into other functional groups, like a lot of different functional groups. So let me show you like basically the scope, right? If I have a vinyl zirconocene, Right, you can turn this thing into a lot of. It's a very very versatile uh, reactant, highly versatile reactant. Uh, well, and it's a precursor to like a lot of different products, right? So here's my vinyl zirconocene here, and so I'm gonna. So here's my zirconium, right? And so if I take that and I can treat it with some electrophile, carbon electrophile, and do a carbon-carbon bond formation, right? I can do a coupling with that. Let me change the color on that. I'll just highlight it, right? So I can couple it with other electrophiles, right? Because you think about that zirconium uh, carbon bond being polarized towards carbon. It is an organometallic, so this is a really good nucleophile, right? I can treat it with another metal, which is a lot of times what happens when you do coupling, other types of coupling reactions. If you treat this with another metal, then you're going to get a transmetallation reaction where the metals just swap out. Sorry about that. I had to zoom in on this because this glove keeps acting up. I said this transmetallation reaction where you can react it with another metal and then end up swapping out zirconium with that metal, right? So now the metal is here. And then whatever the counter ion is on the metal, more than likely ends up on zirconium, right? Another very important reaction that you can do with these vinyl zirconocenes is to treat them with like a carbene and do a carbene insertion, right? So you can even extend the reactivity because of how reactive carbines actually are. Is it everybody familiar with what a carbene is?
Nah, I could use a refresher.
Okay.
Yes, please.
So a carbene looks like I'm going to draw in what the so the carbon right here. This is what we would consider like a carbene. This is a carbenoid, right? It's not a pure carbene because it has a bond to some group. Normally it would be like a diazo, like a N2. It would be like it would be like a heterocycle, but that carbon is what you call a carbene. It has 6 valence electrons, but it has no charge, right? And it can be either what we call a singlet or a triplet, where that what it looks like a lone pair. That pair of electrons can be uh, housed in one orbital because the carbene structure itself looks like this, right? You have carbon, you have here, and then 2 other groups on it. So it can be like this, or it it can be like this. So it can react, and it can react kind of in a polar fashion almost, even though it's not charged. It can be a two electron donor, or it can react in kind of like a radical fashion, where you have an electron um, in each one of those orbitals, right? And carbines are used in lots of different types of chemistry, but the most, uh, probably the most um, prevalent use of carbines is to use them for like cyclopropanations. You use them to form like cyclopropane reactions. If you remember the Simmons-Smith reaction from Organic One, that was a cyclopropanation of an alkene that's using a carbine, right? So it could be what we call a singlet carbine, or it could be a triplet carbine. So this is the singlet, where both electrons are in one orbital, and then this will be a triplet. So it's a carbon atom with a full uh, valence shell, but no charge. Highly reactive species, though very selective too. But you can convert your zirconocene. You can actually insert it into this carbanoid, and you end up with um, this species. So here's your carbanoid right here, and then I'm gonna abbreviate this. Your zirconocene, right? You actually insert into that carbanoid species, right? And you can see again with the carbene having either being either a singlet or a triplet. In this case, it probably reacts as a singlet, where you have a pair of electrons being shared with the zirconium, and then zirconium sharing a pair back, so you can do that insertion, right? Because if you look at where it inserted, you're actually inserting here between the carbon zirconium bond, right? And the carbene carbon will be right here. Right, so that would be your carbene carbon right there, and you insert into that carbon zirconium bond, right? It doesn't seem, interesting, but this is a powerful intermediate, because those carbines can do a lot of reactions, and you can think about the fact that you have a carbon metal bond now. You can still do coupling. You can still use that as a latent nucleophile. So all of that is going to depend on like what you want to do next with this. And you can also oxidize it. You can oxidize that intermediate as well, right? And halogenated. So I'll just draw the halogenated. Um, Come on, stupid glove. Sorry. I'm not going to go Kirk Franklin on my glove, but I sure want to. I think it's because like the material is, I guess, anti-static, anti-palm, but once your hand starts sweating, it changes the uh, reactivity of this material, which is not good. They should have had a liner on the inside of it, but maybe I need to add the liner and then patent it myself, because that's the only difference in from 9 o'clock to now is my hand is sweating a little bit. So and only a little bit. So that means that whatever this thing is made of is really conductive. All right. So that's the utility of your uh, vinyl zirconosines, like, and that's why this reaction is important because you want to take the zirconosine or the Schwarz's reagent with your alkyne, and then you generate an even more powerful intermediate that way you can do all these other reactions, right? Let me show you real quick why alkenes, branched alkene or long chain alkenes won't work, right? And that's why this technology is kind of restricted to alkynes because the alkenes they kind of act up, right? All right, so why not alkenes? All right, so when you take a come on iPad, when you take an alkene and you react it with Schwarz's reagent, I'm gonna show you one example. Uh, but you can take a terminal alkene or you can take a internal alkene. It doesn't matter. Cis or trans doesn't matter. So if you take a terminal alkene like this and you treat it with Schwarz's reagent, right? All you get is this, and that might not seem like it might seem intuitive, but if you take a cis or a trans alkene that's not terminal, you get the exact same uh, product, quantitative yield. So if you take this and react it, you get the same thing. Or if you take this trans alkene, right, you get the same thing. What happens with the trans and the cis alkene is the zirconosine intermediate that you get from that. So I'll put the H down here. What happens is you do what's called beta hydride elimination. So it's going to identify. So there's a hydride here, and in this case, this would be your so this is a beta hydride. Come on, man. Right. So the zirconium can actually do beta hydride elimination, and then put an alkene. Let me get my color together. It can put the alkene here. When remember it was here. Right. So the zirconium can eliminate that hydride that's right there at that beta position, and move the alkene, and then it can add back and do the same thing again. So it does what's called chain walking, right? That's why you don't want to use an alkene as a start material, because that zirconium can walk that whole chain, doing addition followed by beta hydride elimination, and it's just a continuous process. So no matter where your alkene is in the chain, you always end up with this species here as the product, because that zirconium can add and then it can eliminate and it can add back and eliminate again, and it just ends up at that terminal position. It'll walk that chain all the way until it gets to that terminal position. Um, so that's why you don't want to use alkenes as your substrates. You always want to use an alkyne, right? And then we'll talk more about this, and then uh, we're gonna jump into the conformational analysis, because I don't want to leave that out. And then we're gonna come back and start talking about uh, asymmetric catalysis, and then reactions of olefins, so functionalization, like uh, epoxidation and reactions like that. So, anybody got any questions? I apologize the other day about that other video too. It got chopped up, and so all of the lecture didn't get captured, but the notes were decent, so you should be able to follow those.
Okay.
Um, and I'll just write. I'll put this in here. Let me stop recording too, because I don't want all my rambling to be on YouTube.